Hi everyone. In this class, we are going to discuss about inductance. What is inductance? Inductance of a solenoid, inductance of a toroid, and mutual inductance. So first, we are going to discuss about inductance. What is inductance? When coils with n number of turns, it carries current I amperes and it produces the magnetic flux This flux links with each turn of the coil. The total flux linkage of the coil having n number of turns, that is n pi Weber turns. So n pi is the total flux linkage of the coil, where capital N is the number of turns, pi is the flux. The flux linked with the coil is proportional to current flowing through the coil. The flux linked with the coil is directly proportional to the current flowing through it. The ratio of total flux linkage to the current producing that flux. The ratio of total flux linkage to the current producing that flux is called as inductance. Inductance is defined as ratio of total flux linkage to the total current. Symbolically, the inductance is denoted by or represented by capital L. Inductance is measured in henries. Inductance is measured in Henry. So this is the coil. This coil has n number of turns. It carries direct current I amperes. So mathematically, the inductance is L is equal to n pi by I. N pi is the total flux linkage of the coil and I is the current flowing through the coil. So in general, the inductance is also called as self-induct. Solenoidal, in general, the inductance is also called as self-inductance. Inductance is also called as a self-inductance. So next, we are going to discuss about inductance of a solenoid. Consider a solenoid of n turns shown in figure. Let the current flowing through the solenoid I amperes. Let the length of the solenoid is L meters, small l meter, and cross section area of the solenoid is A. Consider a solenoidal. That solenoidal carries n number of turns. The solenoid have n number of turns, which is shown in figure. So this is a solenoidal figure, and it carries the direct current I amperes. Length of the solenoid is small l or capital L meters, and capital A is the cross section area of the solenoid. The magnetic field intensity inside the solenoid is given by H is equal to Ni by L, Henry ampere per meter. The magnetic field intensity inside the solenoid is given by or defined as H is equal to Ni by L. N is the number of turns, I is the current flowing through the solenoid, L is the length of the solenoid. The total flux linkage of the coil. So what is the total flux linkage of the coil? N pi Weber turn. So but flux pi is equal product of magnetic flux density with area. The magnetic flux density is defined as flux per surface area. So therefore pi is equal B into A. N into B into A. But B is equal mu into H. Therefore the total flux linkage N pi is equal mu NHA. What is H? Magnetic field intensity. In solenoidal, what is the magnetic field intensity inside the solenoidal? H is equal to Ni by L. Substitute here. So therefore, the total flux linkage of the coil in solenoid N pi is equal mu N square Ia by L. Next, calculate inductance of a solenoid. Inductance is also called as self-inductance. So what is the definition of the inductance? It is defined as the ratio of total flux linkage to the total current. Total flux linkage to the current produced by that coil. N is equal N pi by I. So that is equal inductance solenoidal inductance L is equal total flux linkage to the total current, that is equal N pi by I. So what is N pi? Total flux linkage. What is the total flux linkage of the solenoid? Mu N square Ia by L divided by I. So numerator and denominator current I is cancelled and the remaining expression mu N square A by L. So this is the inductance of a solenoid. This is the equation of inductance of a solenoid. Next, coming to inductance of a toroid. Inductance of a toroid. Consider a toroidal ring having n number of turns and carrying the current I amperes. Let the radius of the toroid be capital R. Capital R is the radius of the toroid, which is shown in figure. So this is the toroidal ring. This toroid having n number of turns and it carries the direct current I amperes. Capital R is the radius of the toroid. The magnetic flux density inside a toroidal ring is given by or defined as B bar is equal or B is equal mu Ni by 2 pi R. B is equal mu Ni by 2 pi R is the magnetic flux density inside the toroid. Next, calculate the total flux linkage of the toroid. The total flux linkage is N pi, but pi is equal B into A. What is the magnetic flux density inside the toroid? Mu N by 2 pi R. Substitute that value into here. The total flux linkage N pi is equal mu N square I by 2 pi R into A. Here I is the current flowing through the toroid and A is the cross-sectional area of the toroid and capital R is the radius of the toroidal ring. Next, calculate the inductance of a toroid. The inductance of a toroid L is equal total flux linkage to the total current. So what is the total flux linkage? N pi. What is the total current? I. So what is the total flux linkage? N pi mu N square Ia by 2 pi R. Mu N square Ia by 2 pi R divided by I. So numerator and denominator current I is cancelled and the remaining expression L is equal mu N square A by 2 pi R. So this is the equation of inductance of a toroid, where capital A is the area of cross-sectional area of the toroid, cross-sectional area of the toroidal ring, that is pi R square. For a toroidal ring, for a toroid with n number of turns, H as the height of the toroid with R1 as the inner radius and R2 is the outer radius. So in this figure, small r1 is the inner radius of the toroid and small r2 is the outer radius of the toroid. Small r1 is the inner radius of the toroid and small r2 is the outer radius of the toroid. Okay, for a toroid with n number of turns, H as the height of the toroid with r1 as the inner radius and r2 is the outer radius, then the inductance is given by L is equal mu N square H by 2 pi into logarithm of R2 by R. Logarithm of R2 by R. So that is the concept of inductance of a toroid. Inductance, what is inductance? Inductance of a solenoid and inductance of a toroid concepts. Next, coming to mutual inductance. Mutual inductance. Let us consider two magnetic circuits with two magnetic coils carrying two currents as shown in figure. Let us consider two magnetic circuits with two different coils carries two different currents, which is shown in figure. Let coil 1 of N1 turns. Let coil 1 of N1 turns with inductance L1 carries current I1 ampere. Then the magnetic flux produced by current I1 flowing through the coil. Magnetic flux produced by current I1 flowing through the coil 1 is given by or represented by pi suffix 11. Pi suffix 11. First circuit, coil 1, that coil 1 having n1 number of turns with inductance L1 henries and it carries the current I1 amperes. Then the magnetic flux produced by current I1 flowing through the coil 1 is given by pi 11. So similarly, pi22 is the magnetic flux produced by current I2 flowing through second coil. Pi22 is the magnetic flux produced by current I2 flowing through second coil. In the second coil having N2 number of turns and it carries the current I2 amperes and inductance L2. The flux produced in coil 1 also links with coil 2 and produces another flux. That flux is represented by pi suffix 12. Pi suffix 12 is the flux produced in coil 1 also links with coil 2 and produces another flux that is represented by pi 12. Similarly, pi 21 is the flux produced in coil 2 links with coil 1. Similarly, pi 21 is the flux produced in coil 2 links with coil 1. The total flux linkage of the second coil due to the magnetic flux produced by current I1 flowing through the coil. The total flux linkage. What is the total flux linkage? N into pi is the total flux linkage of the coil. The total flux linkage of the second coil due to the flux produced by current I1 in the first coil is represented by N2 pi 12. Similarly, the total flux linkage of the first coil due to the flux produced by current I2 in the second coil is represented by N1 pi 21. Now coming to the definition of mutual inductance. What is the mutual inductance? The mutual inductance between two coils is defined as the ratio of flux linkage of one coil to the current in other coil. Mutual inductance is defined as the ratio of flux linkage of one coil to the current in other coil. So that is the mutual inductance between circuit 1 and circuit 2, coil 1 and coil 2 is given by M12 is equal N2 pi 12 by I1. N2 pi 12 by I1. Similarly, M21 is equal N1 pi 21 by I2. So obviously, pi 21 is the flux produced by current I2 which links with the first coil carrying current I1. If the medium surrounding the magnetic circuit is linear, we can write M12 is equal to M21. The mutual inductance depends on the magnetic interaction between the two currents. Similarly, self-inductance and mutual inductance is also measured in Henry. The dimensions of self-inductance and mutual inductance are Henry. So that is the concept of mutual inductance. Next, coming to coefficient of coupling coefficient. The fraction of the total flux produced by one coil linking a second coil is called as coefficient of the coupling. The coupling coefficient is represented by symbolically K and it is given by or defined as mathematically K is equal pi 12 by pi 1 or pi 21 by pi 2. Take the cross multiplication, pi 12 is equal K pi 1. The mutual inductance M12 is N2 pi 12 by I1 and M21 is N1 pi 21 by I2. Since M12 is equal to M21, M is equal M12 into M21. What is M12? N2 pi 12 by I1 and what is M21? N1 pi 21 by I2. So that is equal M. Here consider M12 is equal to M21. So M12 into M21 that is M into M is equal N2. What is pi 12? K pi 1. What is pi 21? K pi 2. Substitute pi 12 and pi 21 values here. We get M square is equal K square into N1 pi 1 by I1 N2 pi 2 by I2. What is the definition of the self-inductance? N pi by I, total flux linkage to the total current. So N1 pi 1 by I1 is the first coil self-inductance, N2 pi 2 by I2 is the second coil self-inductance. So that is L1 and L2. So therefore M square is equal K square into L1 into L2. M is equal K into square root of I1 I2. Therefore the coupling coefficient K is equal to M by square root of L1 L2. The coupling coefficient is always less than unity. So this is the concept of inductance, self-inductance, mutual inductance, inductance of a solenoid, inductance of a toroid, and coupling coefficient concepts.